Welcome to the course Introduction to Mobile Robotics. Today we begin discussing locomotion control, which is one of the most fundamental aspects of mobile robotics. Whenever a robot receives a command such as move forward, turn left, or follow this path, it must convert that instruction into actual motor movement. That conversion process is what locomotion control handles. Think of locomotion control as a connection between intelligence and motion. High-level algorithms decide where the robot should go, but locomotion control ensures its physically moves in that direction accurately. It regulates speed, direction, and position while maintaining smooth and stable motion. If locomotion control is poor, even a well-designed navigation algorithm will fail. The robot may drift, overshoot its target, or oscillate during movement. Therefore, this module focuses on how robots control wheel motion, adjust steering, and respect physical motion constraints. In short, locomotion control is a foundation that enables autonomous navigation. In this figure, it shows a differential drive robot. A differential drive robot has two independent driven wheels, one on the left and one on the right. Each wheel is controlled separately. This is important because even a small difference in wheel speeds can cause the robot to deviate from its intended path. The architecture shown represents two independent feedback loops. Each loop contains a reference input, a controller, and a motor that mechanical the mechanical system and a feedback sensor. The controller continuously compares the desired wheel speed with the actual wheel speed. If there is any mismatch, corrective action is taken immediately. This continuous correction makes it a closed loop control system. Why is closed loop control necessary? Because real world conditions such as friction, uneven surfaces, or load changes constantly disturb motion. Without feedback, the robot cannot compensate for these disturbances. The architecture forms the core of low-level motion control in most mobile robots. Now let us focus specifically on the velocity control. To maintain a constant speed, the robot must first measure its wheel speed accurately. This is done using encoders mounted on the wheels. As the wheels rotates, the encoder generates pulses. By counting these pulses over a fixed time interval, we calculate angular velocity. The measured speed is continuously compared with the desired speed. If the robot slows down due to external resistance, the controller increases more input. If it moves too fast, the controller reduces the input. Typically, a PID controller is used because it provides stability, reduces steady-state error, and improves response time. Velocity control is especially important when maintaining straight-line motion, synchronizing multiple wheels, following trajectory smoothly. Without proper velocity regulation, the robot's movement would be inconsistent and unstable. Therefore, velocity control ensures smooth and reliable operation. Position control goes one step further than velocity control. Instead of controlling how fast the wheel rotates, we control how far it rotates. By counting in encoder pulses, we can determine the distance traveled or the angle rotated. The controller compares the actual position with the target position and generates corrective action to minimize the error. Position control is essential for tasks that require precision, such as docking, moving exact distances, or turning by specific angles. However, position control is more sensitive than velocity control. Small errors accumulate over time. If the controller is not properly tuned, the robot may overshoot its target or oscillate before settling. Therefore, careful parameter tuning is necessary to achieve smooth stopping without instability. Position control enables accurate navigation and precise motion execution in mobile robots. Next, let us understand how robots change direction. Different types of robots use different steering mechanisms. In a differential drive robot, steering is achieved by changing the relative speeds of the two wheels. If both wheels move at equal speed, the robot moves straight. If one wheel moves faster, the robot curves. If they rotate in opposite direction, the robot rotates in place. In contrast, a car-like robot uses Ackermann steering geometry. The front wheels turn at specific angles so that all wheels follow circular path without slipping. Steering control is not simply about turning, it involves maintaining stability, minimizing slip, and accurately following curved paths. Good steering control ensures smooth transition between motions, reduced mechanical stress, accurate trajectory tracking. The steering control directly affects navigation performance and motion smoothness. Now we have moved to an important theoretical concept, non-holonomic constraints. Non-holonomic constraints restrict motion in certain directions. For example, a differential drive robot cannot move sideways directly. It must first rotate and then move forward. This restriction arises because the wheels roll without slipping. The robot's instantaneous motion is constrained by wheel orientation. This orientation significantly affects path planning and control. We cannot simply command the robot to move in any arbitrary direction. The motion must be feasible according to its mechanical structure. Because of these constraints, trajectory planning becomes more complex. Special control laws are required, path feasibility must be verified. Understanding non-holonomic constraint is essential for designing realistic and physically achievable motion strategies. To control motion effectively, the robot must know its position and orientation in space. This is called the robot's pose. Pose consists of three parameters: x coordinate, y coordinate, and the orientation angle theta. These values are defined with respect to a global coordinate frame. By continuously updating pose using encoder data and kinematic equations, the robot can estimate where it is located. This process is fundamental for navigation and localization. Pose representation allows us to plan path, track movement, correct errors, implement feedback control. Without pose estimation, locomotion control would lack spatial awareness. Therefore, pose representation forms the basis of higher level navigation algorithms. The kinematic model describes how the robot moves based on geometry without considering the forces. For a car-like robot, the turning radius depends on wheelbase, steering angle, and velocity. When the steering angle changes, the curvature of the path changes. The smaller the steering angle, larger the turning radius. Kinematic modeling helps us predict future position based on current inputs. It forms the mathematical backbone of trajectory tracking and control design. It is important to note that kinematics ignores acceleration and forces. It purely focuses on motion relationships. Understanding kinematic models allow us to design controllers that respect the physical limitations of the robot. Now we discuss Dubin's paths, which are used in motion planning under constraints. If a robot can only move forward and has a limited steering angle, it cannot turn arbitrarily sharply. This limitation defines a minimum turning radius. Dubins proved that the shortest feasible path between two configurations under such constraints consist of a combination of left circular arcs, right circular arcs, straight line segments. This means optimal motion is not random but structured. The large circles shown represent the minimum turning capability. The robot transitions between arcs and straight lines to reach its target efficiently. Dubin paths are widely used in autonomous vehicle navigation, UAV path planning, parking systems. They ensure the planned path is physically achievable. To conclude, locomotion control is essential for transforming navigation commands into controlled physical motion. We have discussed closed-loop motor control, velocity and position regulation, steering mechanisms, non-holonomic constraints, kinematic modeling, and Dubin's path planning. Each concept builds upon the previous one to create a complete motion control framework. Accurate locomotion control ensures smooth movement, safe navigation, and reliable autonomy. Without it, intelligent decision making cannot translate into meaningful action. This completes our discussion on locomotion control in mobile robotics.